Welcome to the Mathematics, Society and Education Lecture Series. I'm Xin Yang from the University of Macau, and it's my greatest honor to chair today's lecture. We are really lucky to have a very special guest with us, Professor Zelman Yusiski from the math education professor from the University of Chicago. First, please allow me to briefly introduce Professor Yusiski to you. Professor Zelman Yusiski, as I just said, a math education professor at the University of Chicago. His work has mainly focused on the secondary school mathematics curriculum, but his interests cover all aspects of mathematics education, with particularly emphasize on matters related to curriculum, instruction, and assessment, the selection and the organization of content, the teaching and the learning of mathematics, international mathematics education, teacher education in mathematics, and the history of mathematics education and educational policy. Early in his career, he became known for his curriculum development work in geometry, with real-world applications of mathematics and the using of latest technology into the materials. Ideas gleaned from these studies were among these incorporated in the secondary school materials developed in a very famous curriculum project in the US and also internationally in the University of Chicago School Mathematics Project, which he directed for over 3 decades. He is the author of over 115 published articles and co-author or co-editor dozens of books, including a mathematics textbook for teachers. I know there are some students and also some teachers here, so Professor Yusiski already edited books, not just for students, also edited textbook for teachers. He has received lifelong achievement awards from many organizations, including NCTM and NCSM in the United States, and the International Society for the Design and Development of Education internationally. In 2014, NCTM published a book of 38 of his papers. This is the only time they have published a book devoted to the writings of one person in the US. So today we have a wonderful opportunity to learn from him. His topic for today is briefs about mathematics and the learning of mathematics. I think this is a subject as students, as teachers, and as researchers, we all need to think deeply. Okay, so everyone, please join me. Welcome Professor Zelman Yusiski.
Thank you so much. It's a great honor to have been invited to present in this lecture series. Thanks to Dean Fan and all the others who invited me and approved the invitation. My wife and I have had a wonderful time here. This is an extraordinary place in Macau. You are very lucky to be in Macau. So let me begin. We live our lives based on beliefs. Why do we believe in something? It may be because we have been told this thing by a person or persons we trust, from parents or relatives or teachers or friends or famous people who we have seen in the news or whose writings we have read. It may be because we have seen confirmations of this belief firsthand. It may be because we think that believing is good for us personally, or for our family, or for others we know, or for our city, or our country, or the world. It may be because we've studied the context of the belief and have made a conclusion based on our study. It also may be because we can't think of any alternative to the belief. One thing that is common to all these origins of our beliefs is that a belief tends to be difficult to change. People are reluctant to change their minds even in the face of evidence that a belief held may be wrong, that the belief may be based on incomplete or incorrect information or superstition, or even that the belief might be unwise, leading to an unhealthy situation. Today, I will examine some beliefs about mathematics and the learning of mathematics that have implications for what we teach and how we teach our subject. And obviously, if they have implications for what we teach, they have implications for what we learn. Some of these beliefs are common in the United States and some other countries, but may not be as common or even believed at all in Macau, throughout China, or East Asia. I will touch on beliefs related to what mathematics is, who can do mathematics, the learning and teaching of mathematics, and the school mathematics curriculum. In the time we have, I can only mention a belief or two in each category, and even the most that can be done is to raise some issues and perhaps provide a few insights. First, what is mathematics? I begin with one of the most famous quotes of all time about mathematics, expressed 400 years ago by the Italian polymath Galileo Galilei in his work Il Saggiatore. Translated into, I won't try to read the Italian, but translated into English literally, mathematics is the alphabet in which God has written the universe. A common translation omits a reference to God. The universe, or sometimes nature, is written in the language of mathematics. And Galileo goes on, its letters are triangles, circles, and other geometrical figures without which it is humanly impossible to comprehend a single word. I believe in the spirit of this quote and in the fundamental importance it gives to mathematics. It is amazing to realize that Galileo wrote this before the discovery of the physical laws involving gravity, before the discovery that the planets revolved around the sun, in such mathematical orbits that we could predict exactly where a planet is going to be, even many, many years from now, before the discovery of DNA and how genes transmit information from generation to generation in all living things, and all this centuries before computers and all that computers can do. And in the world of mathematics, it was before what we consider to be standard content in calculus, linear and abstract algebra, non-Euclidean geometries, differential equations, topology, and a myriad of other subjects. It is also the case that the letters in the language that Galileo speaks of include a far broader range of figures than the triangles and circles and the ellipses of orbits. Today, the figures studied in mathematics include spirals and all sorts of surfaces, graphs of functions, and of data, and networks, and fractals. The breadth of applications of mathematics has led more recent mathematicians and mathematics educators to think of mathematics as a study of patterns, or as the science of patterns. This view, that mathematics is the study of patterns, is often attributed to have been asserted first by the British mathematician Geoffrey Harding. It has been stated since by many others, including me, in the title of a section in a first-year algebra text for 8th or 9th grade in the United States, and reflecting a view that real-world uses of mathematics should be employed to introduce mathematical ideas in the curriculum, rather than just to practice the mathematics. A view that has become increasingly popular since. More famous people have held this view. W.W. Sawyer, Lynn Steen, Keith Devlin, Michael Fried all have writings whose title speaks of mathematics as the study or the science of patterns. At the time of Galileo, the language of mathematical discovery was different in different parts of the world. But today, the language of mathematical discovery has become much the same worldwide, just as what has happened with much of music and much of sport. The universality of mathematics is, as much as any other quality, the quality that makes me proud that somehow I fell into mathematics as the setting for my career, and makes me happy to try to transmit mathematics to others. And it's this universality that enables me to come halfway around the world to speak to you on the subject. If mathematics is the language of the universe, and since almost everyone learns their native language, it seems natural to expect that everyone could learn this language rather well, and learn it rather easily, without much work, as easily as learning to speak. Equivalently, if mathematics is the study of patterns, and there are patterns everywhere, it seems that people would see these patterns and want to study them, and thus be immersed naturally in the study of mathematics. But this is not the case. Many people, perhaps the majority in some countries, believe that people differ innately and substantially in their ability to learn mathematics. By substantial differences, I do not mean the kinds of differences like the physical variations in height that we expect from any population, but substantial differences such as the absence of a limb that presents physical limits on individuals. In the United States, these beliefs that mathematics ability is innate are directed at two populations. First, that boys have greater ability than girls. Second, that certain ethnicities have greater ability than other ethnicities. And one can look rather easily for evidence that supports these beliefs. Not just a little evidence in one place, but what seems to be definitive evidence. But as in many nature-nurture questions, the situation is not so simple. Many reasons are given to believe that engender differences in the learning of mathematics. I'm here just repeating many things you know. The overwhelming majority of famous mathematicians in the world have been men. The overwhelming majority of mathematical Olympiad participants are male. Occupations that require a great deal of college-level mathematics tend to be populated in most countries more by males than by females. Or maybe, there are differences, but they're like those in athletics, where the very fastest men outrun the very fastest women, but most women, the fastest women, can outrun almost all the men. But as you know, there are reasons not to believe in gender differences in the learning of mathematics. Though the most well-known mathematicians in history are almost all male, until recently, women were not offered either the education or the opportunities that men could have. Even so, there were world-class women: Hypatia, Emmy Noether, Ada Lovelace. In recent studies in the United States, around 30% of all doctorates in mathematics are to women. And that's to US citizens. I'm not talking about people who come to the United States. And that figure has remained relatively constant for the last 15 years. Many societies view the competition that Olympiads require as more for boys than girls. And many countries, some occupation categories are much more with women, populated by women than men. While in other countries, the same occupations are occupied by men more than women. So these differences don't necessarily mean that they're universal. And the differences are not consistent around the world. A UNESCO study combined data from the Latin American Laboratory for the Assessment of Quality of Education, the Programme des Systèmes Éducatifs de la Conférence, that's French, Southeast Asia Primary Learning Metrics, and TIMSS surveys. That's the International Studies of Mathematics and Science. And involved a total of 120 countries. Most of the data comes from before the pandemic. This slide shows 3 of the findings. In the early years, boys perform better than girls, but this gap disappears later. In some countries, girls perform better than boys. For instance, at grade 8, girls perform better in Malaysia, Cambodia, Congo, the Philippines. And what we see in the Olympiads is reflected in the results of this study, namely that among the highest performers in all countries, boys are more represented than girls. I might be inclined to conjecture that there might be a slight innate gender difference if I did not know the situation of the startling change over time in the gender composition of the highest realms of music performance, namely in the players of the major symphony orchestras in the world. The New York Philharmonic Orchestra, the major orchestra in New York City, was organized in 1842. You can figure it out, it's 183 years ago. Is my mathematics right? But the first woman to be a member of that orchestra was not until 80 years after it was formed, in 1922. It was all male until 1922. She played the harp. You know the harp. She was only in the orchestra for 10 years. She resigned. She was not let go. She resigned. The next woman in the orchestra was a double bass player in 1962. So for another 30 years, there were no women in the orchestra. But in 2022, the orchestra had 89 members, 45 were women, 44 were men. Such a difference. Now, the Chicago Symphony Orchestra, which we believe to be, of course, the greatest orchestra in the world, has 81 people listed in its roster, and there are 51 men and 30 women. It's not as equal as the New York. And I attend that orchestra regularly, and I can tell you that the women are generally centered in the violin and viola sections for more than any others. There are women sprinkled through the other sections, and the women are, at least half of them are Asian. Here is a picture of Leonard Bernstein, famous conductor of the New York Philharmonic Orchestra, but not with the New York Philharmonic, but with the Vienna Philharmonic, which at the time was probably considered to be the best orchestra in the world, in Vienna. There's no woman in the orchestra. It's 1966. Not until 1997, 31 years after this picture, did the Vienna Philharmonic Orchestra have its first woman member. Again, a harpist. This orchestra, as a private organization, not a public organization, argued that it was not required to have a woman member. You could not get away with that today, but we don't have to, so we're not going to have one. But public outcry and boycotting of the orchestra led to the change. But even today, it's male-dominated. Only 24 out of 145 members in the orchestra, 24 out of 145 are women. In the US, the gender balance in orchestras has been more significant and began in a different way. Beginning in the 1970s, due to requests for equality, the audition rules for the major US orchestras changed. Instead of seeing prospective players when they auditioned, the players were required to play behind a screen, and their names were anonymous to the selection committee. Significantly, women were told not to wear shoes with heels. You understand? So you could not tell the gender. As a result, the selections were made based only on the sound that the musician would produce, and gender did not play a role. The result 5 decades later is that it's now estimated that 47% of the musicians in the major orchestras in the United States are women. It's virtually the same. If you're acquainted with the history of classical music, then you know that female composers, such as Fanny Mendelssohn, the sister of Felix Mendelssohn, the famous composer, put his name on some of her compositions so that they would be played. I mean, women just were not recognized for centuries for our accomplishments. Only in recent years have we begun to hear a significant number of compositions written by female composers, some having been composed recently, but others having been composed 100, 150, 200 years ago and never played. Beliefs about gender differences cause gender barriers to be difficult to break. The picture of the Vienna Philharmonic reminds me of this picture. It's from the First World Congress of Mathematicians, which occurred at the World Columbian Exposition in Chicago in 1893. All men. There's not a woman in it. This is the first Congress of Mathematicians, all men. In fact, you might argue from this picture that in order to be a mathematician, it's helpful to wear a beard. Only 2 people in this picture, I think, do not have a beard. In the middle of the picture, the very middle, with the white beard, is Felix Klein from Germany, who gave the major address. It was at this Congress that plans were made for the first official International Congress of Mathematicians, today called the ICM, which occurred in Zurich in 1897, 4 years later. Of the 208 attendees in Zurich at the first International Congress of Mathematicians, 4 were women. 203 were men. It is clearly a different world today in mathematics and in music and in many other activities. It teaches us that even long-held beliefs can be changed. A variant of the belief that your gender affects your ability to do mathematics is that your ethnicity affects that ability. In the United States, in my generation, it was the Jewish students possessed greater natural ability. And I'm in that generation. So in some sense, it was an advantage to me because of course, he's good in mathematics, that kind of thing. In the current generation, it is that East Asian students are naturally better. We who are members of these ethnic groups, and virtually everybody in this room is a member of either one of those, not everybody. We know it to be a false belief. It devalues the amount of work that it takes to gain mathematical competence, and it's often a sign of racial or religious prejudice. Now I move to a belief in a different but related area, from who can do mathematics to how math performance is judged. A common belief is that the faster you can do mathematics, the better you are at mathematics. You may think, well, no one really believes that, but practices throughout the world reinforce that belief. Classroom tests typically have a time limit. And so do standardized tests in the United States, which are often used to sort students. But I have been told that the state of Texas, in its most recent state test, allows virtually unlimited time for students to do their state test. Very unusual, exceedingly unusual. Tests for college admissions have time limits. And they're important tests. Mathematics contests sometimes have severe time limits. In fact, the Olympiad competitions with very difficult problems, might say, have the most severe time limits. Because for most people, it might take days to solve a particular problem, and you're given 3 hours or 3 hours and 15 minutes, that's all. A study, an interesting study, which just showed, maybe you shouldn't believe every bit of research, but this is an interesting little tidbit. It was a study of first-year medical students, which, judging from the names of the authors, was in India, found that both the visual and auditory reaction times among the female students were about 6% slower than their male counterparts. Now let's understand, this is first-year medical students. These are good students. They're all good students. You would not think that reaction times should be different. Is it possible that this small difference in reaction times reflects a small difference in speed of thinking and is not particularly significant on classroom tests? or typical standardized test but comes into play in the mathematical Olympiads? Is that possible, just that little different? Or are visual and auditory reaction times not related at all to the processing of mathematical information that occurs in solving problems? Or is this an artifact of how the men and women in this study were raised when they were children? That the boys were kind of given things that expected to do things faster? We do not know. Relating to the importance of speed in mathematics, now I've added to the previous slide, it's useful to repeat what has been said by Andrew Wiles, who produced one of the great achievements in mathematics research in the last half-century in 1994 by proving Fermat's last theorem, having worked for 7 years on this problem in private. He emphasized that a mathematician is defined by patience, perseverance, and accepting that you may be stuck, but continuing to work to understand a problem in order to come up with a solution. For the students in the back, this is a very important quote. Perseverance and patience. You don't have to get the solution right away sometimes. A person does not have to be a great mathematician to feel this way. The first time that I spoke at a professional meeting was when I was 20 years old, in my last year of college. It was a meeting of the Illinois section. I'm from Chicago, is in the state of Illinois, and the Illinois section of the Mathematical Association of America. This is an organization of college-level mathematicians, not necessarily research mathematicians, but people, many of them are, but many of them aren't just teaching at college level. The speakers were undergraduate college students like me, who had done original work in mathematics. Each student was given about 10 minutes to explain their work. I started my presentation by showing a stack of paper about 2 centimeters thick. And I said something like, this work took me months, and they expect me to explain it in 10 minutes. It got a good laugh. This was the first one. Now let me turn to the learning and teaching of mathematics. Beliefs about the learning of mathematics are what influences curriculum. About the learning of mathematics influence curriculum. Beliefs about the teaching of mathematics influence instruction. A very common belief is that it's better to learn mathematics from the ground up. That is, from the mastery of basic skills first, then to gradually increase the sophistication. A variant of that is that we learn in stages. And the stage of an individual is it limits what a person can learn. The most famous stage theory, well, there are 3 of them, was that of Piaget, developed in the 1920s, but published in the 1930s in France. Piaget's work led him to believe that brains develop in stages, biologically determined from the concrete, also called the sensory motor, to pre-operational, these are names that were given and translated into English from French, to the operational, to the formal. When I was a student, Bruner's theory of learning became popular. It was that children learn in stages, a little different, that they learn in stages, different from brains develop in stages. It was that children learn in stages. From concrete to iconic to formal. Bruner's theory was in opposition to another theory that's not on this slide because it's not a stage theory, and that was B.F. Skinner's stimulus response theory, which is that behavior is learned by reinforcement of desirable consequences, and is not a stage theory, as I said. It's interesting that Bruner and Skinner, probably the 2 most famous psychologists in the country at the time, were both at the same university at the same time. They were both at Harvard. That we learn in identifiable stages seems so self-evident that it's often not questioned. But the history of mathematics indicates that the discovery of mathematics does not follow these stages. There have been many occasions where the mathematics exists in theory without any concrete application, and only later do we find concrete examples. For example, prime numbers and abstract algebra were studied well before their use in developing codes, code theory, information. And I learned about the concept of area in geometry well before I ever measured the area of anything real. Indeed, when I taught geometry in high school, early in my career, I would draw an arbitrary triangle. We'd copy this triangle for the students and say, here's a triangle. What's its area? So they had no way, they couldn't do it. We had no concrete knowledge of what area they could. You give them the formula, they can calculate the area of triangles, of any triangle. If you give them the base, give them the height, give them this, but their actual knowledge of area, of what it was, and what might be bigger area, and what might be smaller area, just visually, was not developed. So I felt, and this is the way I learned, I felt I actually went from the formal to the concrete. I didn't learn from the concrete that particular concept. So I'm kind of a skeptic when it came to the stage theory. I may be overstating this point. There's something rather elegant about dealing with abstractions and then later finding out that they have applications. Now allow me a digression, a personal story. You have to allow me, you're trapped. I received tenure at the University of Chicago about 50 years ago, which is quite amazing because I'm only 46. But I know how to subtract larger numbers from smaller numbers, so it all works. Slightly after I received tenure, I was asked by the University of Chicago Press to examine a long manuscript, over 700 pages, that had been translated from Russian to English by the Survey of East European Mathematical Literature at the university. It was a survey to translate Soviet materials. The directors of this survey were Isaac Virzhub, a mathematician at the university, and Jeremy Kilpatrick, then a young professor at Teachers College, Columbia University in New York. Some of the people in mathematics education know of Jeremy. It was a long manuscript, as I say, over 700 pages. And the University of Chicago Press, which is a major university press in the country, wanted to publish it, but they felt it's too long. Nobody will read 700 pages. Can you shorten it? Can you get maybe 200 pages? They specifically asked me to suggest what should be cut from the manuscript. I read the manuscript and gave my opinion that it was extraordinary from beginning to end and should not be cut at all. And so the translation was published in its entirety. Some of you may know of this book, some of you in the field. It's The Psychology of Mathematical Abilities in School Children by V.A. Krutetsky. It's known as Krutetsky's work. It begins with a detailed put-down of Piaget's theory. The first thing it does is Piaget's work. It conforms with Soviet political policy by calling children capable and very capable rather than gifted. You never see the word gifted. It contains a startling collection of ordered problem sets that were given to children. For me, the most interesting concept in the book was called curtailment. Curtailment. The skipping of steps that very capable students manifest, generalizing well beyond the expected. My understanding is that there was no obvious English word for the Russian that became curtailment. The Russian word for this, there was no English word. And it was Jeremy Kilpatrick himself who suggested, let's call it curtailment. It's a brilliant choice. A key takeaway for me from this book was that the order in which we pose questions and problems to children is critical in their learning because generalization and extension are natural human characteristics. Not long after the publication of the Krutetsky book, oh, sorry, I got ahead. Oh, I don't want to tell you what I believe. Hold there for it. Wasn't Isaac Virzhub, the same person who was the head of that other project, started touting a stage theory developed in the 1950s by Dina van Hiele Geldof and her husband Pierre van Hiele. It was that geometry and other formal mathematics is learned in 5 stages: visualization, analysis, informal deduction, and rigor. Virchow reported that Soviet academicians had utilized the von Hiele theory in their curriculum work in geometry. I was skeptical because I told you the story. Also, as a geometry teacher in high school, so we at Chicago became one of 3 projects to test the von Hiele theory. We created a 25-question multiple choice test, 5 questions on each level to test for a student at that level. In order to be at a level, you had to answer correctly the questions below that level. Otherwise, it's not a level theory. So the idea is if you can answer 4 out of 5 questions at the lower levels, then you're at that level, and maybe if you're at level 3, you should be able to answer the questions of level 2 and level 1. Von Hiele himself came to the university to look at a draft version of the test, and he guided us to have appropriate questions for each level. We called it the von Hiele geometry test. We gave the test twice to about 2,400 students in 13 schools in 5 states in the United States. Once at the beginning of the school year, once at the end. Would students who correctly answered questions at a level also correctly answer questions at each lower level? And could we verify the theory for that student? This was an admittedly very rough test of the theory. We found that about 70% of students answered questions as if they'd gone through the theory. And if we loosened criteria, we could raise the percent. We also found a large percent of student responses put them at low levels of the theory, too low to comprehend the nature of proof that was in most of the geometry courses taught at that time. The ultimate conclusion was that the von Hiele theory described nicely where a majority of students were in their development of geometric thinking, but it did not describe everyone. Is the performance of the majority confirming the levels because they were taught in the rough order of the levels, or because brains evolved in that order? And was the reason many students' responses didn't follow the levels in our study not due to lapses in the theory, but because our test was not long enough or detailed enough to accurately detect the levels? The other projects that were funded used interviews, we used tests. So what do I believe? If we teach in accordance with actuating belief in consecutive stages of learning, if you go from concrete to where, it's to be expected that students will learn mathematics in the order of those stages. But if you avoid the stage, if you decide I'm going to go formal first, maybe students will learn in that order. Allow me to modify the scene slightly from stages to perceived difficulty. And now I want to speak particularly of the early grades. As you may well know, the United States as a whole does not perform as well as Macau or Hong Kong or Shanghai on international tests such as PISA or TIMSS. That's the third international, or the International Mathematics and Science Study. I believe one reason for this lack of performance is that it's normal for primary school teachers in the United States to choose the grade they want to teach on the basis of the level of mathematics that they feel comfortable with. And some of them will only teach grades 1 and 2 and 3 because they don't want to teach fractions. They're not comfortable with fractions. In the highest performing countries, mathematics teachers teach even starting in grade 1. Fundamental difference in what you get for expectations of the students. Even those in the United States who teach in grades 4 and 5 tend to believe that mathematics is more difficult than reading. I try to disavow teachers of this belief by taking 2 examples of reading that demonstrate the difficulty of reading English. I will not even attempt to talk about the difficulty for someone like me to read Chinese. Absolutely impossible. And yet all of you, or almost all of you, do. The first example I'd like to give is the word mathematics. Mathematics is more difficult than reading. Just reading mathematics, just that one word, mathematics. the M, the A, the T. The TH is not the T. There's no T sound in mathematics at the beginning. It's th. And it's not a the, it's th. There's two sounds to th. And the E does not sound like it's not, it doesn't sound like E or eh, it sounds like meth, and the MA it's easy. The T is easy. The CS at the end sounds like X, or separate the C from the S, mathematics. I mean, just this one word is very difficult. Or consider the following, which is and that is, what is O, how do you pronounce OU? Do you pronounce it as in thou? Is it ow? Or is it pronounced O as in though or do? Or is it pronounced ought, as in thought and bought? Is it aw? Or is it oo as in through? Or is it uff with the GH? Is it as in uff? And the GH doesn't, the GH sounds like F. There's no F there, but it sounds like F. And then we have cough, which is, there's another aw, but it's off. And that last one is hiccup. It's not hiccough, it's hiccup. And anybody who thinks that mathematics is more difficult than reading, it's just, how much time do you spend teaching reading and how much time do you spend teaching mathematics? If a teacher believes that mathematics is more difficult than reading, the learning of students will be diminished because the teacher will be more content with students having difficulty with mathematics than it would be content with students having difficulty reading. But how should a teacher run a class? So there's often a kind of two roles of the teacher. These roles have nice sounding titles. One is the sage and the stage. The sage, I'm the sage on the stage here. You don't see me going around looking at, you're not taking notes, and I'm not going around looking at your desks. Where you have desks right there, you could, right? I mean, you could get that, that's right. Or the guide on the side. The guide on the side is the teacher that does, in fact, walk around the room, looks at work, and so on. My feeling, knowing no data, I don't know much data about this, is that in the elementary grades, teachers tend to be more likely to be the guide on the side. But certainly in college, teachers tend to be more the sage on the stage. And somewhere in secondary school, there's a kind of combination of these. And these days, there's much more guide on the side because of technology. The use of technology has changed the role of the teacher. What do I believe about this? The effective teacher moves back and forth between a teacher-directed classroom to one that's more student-centered, depending on the curriculum and objectives for the lesson. You move back and forth. That's the effective teacher. You need to be both. At times you have to be the sage on the stage. Much of the time, guide on the side. This is my sneaky way of segueing into the curriculum. People who study curriculum, and this is where I've spent most of my career, distinguish between various types of curriculum. In some international studies, 3 types of curriculum are identified and studied. The intended or ideal curriculum, based on official documents of the school or school system. The taught curriculum, based on classroom reports and observations. And the learned curriculum, based on results of tests, of written or oral assessments. Some people differentiate 2 other types. The materials curriculum, namely those materials that are available for students and teachers to facilitate learning, and the tested curriculum. That is the content that is on the tests in their classrooms. It's perhaps too simple, but the ideal situation is for all 5 of these curricula to be in consonance, to somehow agree with each other. And note that it takes different kinds of research to study these 5 different types. The intended curriculum can typically be found these days from documents online. The materials curriculum requires finding and examining textbooks and supplementary materials, both in print and on websites. The taught curriculum requires classroom observations to be done right, because teachers' self-reports are not always accurate. The tested curriculum, like the ideal and materials curriculum, requires finding documents, but the tests are often not public. It's hard to find the tests. And the learned curriculum requires that students be tested and results analyzed. These different types mean that studying curriculum is very complex. And then a sixth type of curriculum is sometimes the hidden curriculum. The hidden curriculum refers to the content and attitudes that students acquire from their school experiences that are not tied to the original goals, the materials, and what is taught. Often attitudes and beliefs are usually a part of the hidden curriculum. My work, and I might add the work of my wife who's sitting here, throughout the career, and she's still working full-time while I just give talks, has been most visibly with the materials curriculum. But unlike her work, which has been for commercial publishers and ruled by the intended curriculum, my work has been to develop materials that might influence changes in what mathematics is intended, what mathematics is taught, and what then, obviously, what mathematics is learned. I would like to discuss 3 areas of this work because each of these areas created an environment different from common beliefs, to change the beliefs that people had towards that area. The first, I will proceed in the order in which my beliefs changed, and the first is about geometry. The geometry that I studied in school, and I guess I'm going to go back up, because you shouldn't read that yet. I'll get to it in a second. The geometry that I studied in school, that I taught in my first years of teaching, was based on Euclid's Elements. It was not in Greek. It was in English. Just so it was based on Euclid's Elements. Congruence was associated with triangles. Is that familiar to the students? If you think of congruence, do you think of congruent triangles? I'm not getting any nods from the back. You don't hear. Oh, I got one nod. One nod is enough. As a master's degree student at Harvard, I was introduced to the approach taken in one of the new math materials, which took a more rigorous approach to the subject while keeping the same theorems. In this approach, there were different definitions involving congruence for segments than for angles. Segments were congruent if they had the same length. Angles were congruent if they had the same measure. Triangles were congruent if you had a relationship between the vertices such that the sides had the same length and the angles had the same measure. In my schooling, the ideas of congruence and similarity had only applied to triangles, not to segments, not to angles. Congruent triangles were perhaps the major topic in the proof development, important for their apparent applications to the study of quadrilaterals and then to the study of similarity in circles. However, except for the area and volume formulas, none of this content seemed relevant for later mathematics. I never used congruent triangles in calculus. Huh? Why did we spend time studying it if I never used it? This was supposedly my most important course, first course in college mathematics. And I felt this was a major deficiency of the geometry course. And the geometry course was occupying an entire year of the school curriculum. Allow me an aside. In 1991, in my first visit to China, 1991 is the old China, I visited an 8th grade class in Shanghai. I understood nothing that was being said by the teacher or the students. Absolutely nothing. But I saw on the chalkboard what seemed to be a geometry proof. You know, a column, it had a line between, it looked like there were statements here. I did not know what the proof was about because of my total inability to read Chinese characters until the 3 letters SAS appeared. Side, angle, side. Congruent triangles. That's what they're studying. it's world mathematics. I said, mathematics is a worldwide language, but I didn't expect an English abbreviation to sneak into what was entirely in Chinese. It's kind of just an aside, says in the system. Then, as a doctoral student at the University of Michigan, I was introduced to an idea that Felix Klein had spawned a century earlier. In his Erlangen program, the basing of geometry on groups of transformations. I loved abstract algebra and group theory, but it was not the group theory that attracted me. It was that the single definition of congruence in terms of distance-preserving transformations, which was both elegant and intuitive. And those two words, elegant and intuitive, do not always appear together. This changed my belief regarding the scope of applications of geometry, widening it to realize that every physical object is geometric and thus subject to the ideas of congruence and similarity. This allowed geometry to be applied throughout mathematics. As a bonus, the intuition that came with using transformations made the content more accessible to slower students. The elegance of a transformation approach gave a weapon for future mathematics, most obvious with the graphs of functions that students would see in algebra. In partnership with Arthur Coxford, my thesis advisor, my doctoral dissertation involved writing and testing a full course for typical geometry students that used this approach. And our text was published in 1971, when you can figure out, I was 12 years old. And all my later work in geometry has used this approach. But change is slow. It took until 2010, almost 40 years after our text was published, for the major intended curriculum in the United States, the Common Core, to say that congruence and similarity should be developed through transformations. But from my days here, I think this approach is not known in China. So I will explain in just a couple of slides how the definitions and theorems of congruence and similarity change with this approach. Just 2 slides. So here's the first. Now we deal with any set of points. Any set of points is a figure. They can be discrete points, they can be connected, they can be a region, they can be any set of points. And 2 sets of points, 2 figures, are congruent if one is the image of the other under a distance-preserving transformation. Reflection, rotation, translation, or implied reflection. It happens that all 4 kinds can be developed through reflections. If you combine 2 reflections, you can get a rotation, you can get a translation, and you combine a translation with a reflection, you get a glide reflection. The triangle congruence theorems, all of them can be deduced, whereas under most of the developments, SAS was taken as a postulate. It's not a postulate in this approach. It's proved from postulates about transformations. All graphs being sets of points are figures, and they bring algebra into the picture, particularly graphing. So now a graph is a set of points, and those are geometric points. And then there are a couple of theorems, and one of the basic theorems about graphing is what we call the graph translation theorem. If a set of ordered pairs, x, y for a function or relation, x is replaced by x minus h and y by y minus k, then the graph is translated h units to the right and k units up. The language of transformations gives you a language to understand why the parabola y equal x squared is congruent to the parabola y equal x squared plus 5, or y is congruent to the parabola y equal x minus 3 quantity squared plus 5. It's a translation, it's just the image under the slide. Now all circles with the same radius are congruent and all their equations easily deduced. If you have an equation for the circle with center at the origin, you can translate the circle easily to any center. So it explains a lot of formulas. Then I said 2 slides, so one was for congruence and this one's for similarity. 2 figures are similar if one is the image of the other under the composite. So now we throw in a dilation, or what's sometimes called a dilatation. We called it a size change. We liked a simple word. So you combine now a size change and you've magnified the figure, and you magnify it, now you get similar figures. And now you can deduce SAS similarity from SAS congruence quite easily, and SSS from SSS congruence, and angle comes from the angle side angle congruence. That's how you get angle. Then there's also a graph scale change theorem that is an analogy to the graph translation theorem. And this what happens when you stretch. And if you want to think of the most common example of stretching, it's to stretch a circle into an ellipse. You take perpendicular axes and stretch them. So if you replace x by x over a and y by y over b, then the graph is stretched a times horizontally, b times vertically. And if you know the equation for an ellipse, you can see where it comes from. It comes from this stretching. And that's number 9 here. And then applying the scale change, just a scale change, just a one dilatation. So let's say y equal x squared. What you find out is that all parabolas are similar. Even the ones that look like this and the ones that look like this. They're all similar. How can all parabolas be similar if some look like this and some look like that? The answer is take a magnifying glass around the vertex. And when you take a magnifying glass to that vertex, you find out that what was this in the parabola looks like this. This parabola is just bigger. You're seeing less of it on your graph. You're seeing less of that parabola on your graph, and you think that in fact it's wider and not, but in fact it's just bigger. They're all similar, all parabolas. And in general, 2 conic sections are similar if they have the same eccentricity. And all parabolas have the same eccentricity. After I got my doctorate, I got a position at the University of Chicago as an assistant professor. For all the time, I'm looking at the time. For all the time I was at this wonderful institution, and the University of Chicago is an incredibly wonderful institution. There was one other faculty member in mathematics education. That colleague, Max Bell, believed not only that it was important to teach real-world applications of mathematics, but that the standard word problems found at that time in the study of algebra, problems involving coins, you had coins in your pocket and they had a total value of such and such, how many coins did you have and what was their total value, and figure out how many of this kind of denomination and that kind of denomination, that kind of problem. A phony problem. They're not applications because in order to make up the problem, you have to know the answer. You know the answer first, and then you make up the problem. This is not the way the real world works. And he felt it, I think correctly, that it actually had the effect of teaching students that mathematics had no meaningful real world applications. In the late 1970s, Max and I combined with National Science Foundation support to write a long work on the applications of arithmetic. Our analysis of the applications of addition and subtraction indicated that the major applications of addition and subtraction were well positioned in the curriculum, well taught. Students were well taught addition and subtraction, but it disappeared with multiplication, because multiplication was taught as repeated addition. Multiplication was not given its rightful place as having applications that were not repeated addition, not anywhere close to repeated addition. When you got to multiplication of fractions, you were in trouble because you couldn't, how do you get repeated addition, that sort of thing. Division related to multiplication. The goal of our work was to place uses of arithmetic beside the theoretical properties of the operations such as commutativity and associativity. And if you'll notice here, you see in addition, I've listed, for addition and multiplication, I've put the basic applications in red. For addition, we felt there are 2 kinds, putting together and shift. This is well taught. Maybe not called this, Putting together, yes, but not shift, whatever it's called, slide, sometimes it's called slide. But multiplication, we had these three basic applications of multiplication that were not taught. Size change sort of, that we would have with transformations was related to the size change of transformations. Acting across, which is like area, this gets us area, where length acts across width, and really builds you up for calculus. And this is where it comes from. And rate factor, which actually is sort of coming from rate in division, and division as ratio and rate, rather than just splitting up. Taking it out of just whole number applications, and often small whole number applications, into the broader range of things. We called these things in red, and I didn't put the ones for subtraction and division in red, but we called those use classes. Today, we would call them models. The language of mathematical modeling was just not around when we did this work. Did it before that. As a final look at beliefs regarding curriculum, I want to talk about technology. This is the last part of my presentation. We'll wait for that. Technology raises questions that began in earnest when the first handheld calculators appeared, 1971. Early 1970s, they were expensive. Very quickly, the price came down. They were believed by many to be dangerous. They would spoil the understandings of arithmetic that comes from paper and pencil computation. That's the way you understand arithmetic. That was a belief. I suppose that parallels the belief of many when the first automobiles appeared, that the dangers of automobiles outweighed the advantages. They were quite dangerous at the beginning. For automobiles, we built roads to make travel easier and driver training courses to educate people to use them. The corresponding reality today for classrooms is that, like automobiles, calculators and computers carry us to places that are hard, if not difficult, to reach without them. Very similar in a way. So it's wise to use all this technology, but we must teach children, just as we teach drivers to drive carefully, we must teach children to use them wisely. This goes for four-function calculators, graphing calculators, computer algebra systems, graphing utilities, and so on. But today I don't hear people talk much about calculators and computers and that sort of stuff. All the talk is about AI. How AI is being used for all sorts of tasks teachers have done, to create lesson plans and even script entire lessons, to create exams, to grade exams, and so on. And also to solve quite difficult mathematical problems, and even to discover new mathematics in the process. Here is, just so you all know, just so you know, this is an AI response. I thought it was cute. Ask AI, what is AI? And this is the answer, this is the Google answer to what is AI. You know this, of course. AI performs tasks typically require human intelligence, such as learning, problem solving, decision making, recognize patterns. Wait a minute, patterns. Isn't that mathematics? Oh my. Understand, respond to language. Isn't mathematics a language? This is Galileo, and this is the mathematics is the study of patterns. It's sitting here. Make predictions, generate creative content. The biggest problem with AI is that we don't know what was inputted to arrive at the output. With a calculator, you yourself press the buttons, you yourself do the inputs, and you get an answer that comes back to you. In AI, you don't know how that answer was gotten. Sometimes the AI tells you sources, but how did they pick the sources? How are they doing the search to get this? I wish they're doing very quickly, I might say. So I thought you might be interested in this quote that I found while creating this talk. And it's from a recent, you can see the article is just from October 26, so it's just from a few weeks ago. The challenge is how to keep human agency intact, how to remain the authors of the systems that are now poised to take on so much of our thinking. Each generation has had to learn how to work with its newly acquired cognitive prostheses, whether stylus, scroll, or smartphone. What's new is the speed and intimacy of the exchange, tools that learn from us as we learn from them. Stewardship now means ensuring that the capacities in which our humanity resides, judgment, imagination, understanding, stay alive within us. If there's one skill we cannot afford to lose, it's the skill of knowing which of them matters. So it seems to me those things are the essences of mathematical thinking. This gets us back to the beginning of the talk. And that is, the essences of mathematics, the importance of knowing carefully what words mean, what things mean, the need for assumptions about these terms, to implicitly tell us what they mean, deduction from them. This is what mathematical thinking is, and it parallels what we need in order to understand the latest in computer science and information sciences. And highlighting common areas. This is what mathematics is about. Mathematics is about careful thinking. Mathematics operates in a world in which the language and logic are subject to strict rules. And that's the benefit of mathematics. We know the rules. We know the strictness of the rules. We are not just given information. We know we can test the information. We can check the information. This is very important. Mathematics gives us tools for that. If we believe statements A, B, and C, and from those we can deduce statement X, we know we should believe statement X. And we're aware of logical fallacies. We know that one counterexample is enough to destroy a generalization. This is important. We know that if A implies B, that doesn't mean that B implies A. Or that not A implies not B. Neither one of them. These are the kinds of things that we need to make sure that we don't forget when we're teaching students to solve problems, but there is a mathematical thinking behind it. So, as Galileo wrote, mathematics is the language of the universe, with applications everywhere, and yes, mathematics is the study of patterns, beautiful mathematical and beautiful numerical and geometric patterns, and structural patterns we call morphisms. But in all this, what makes mathematics distinct is the logic by which mathematics operates and the openness of mathematical thinking. These are the qualities that lead us to believe in the results, some rather obvious, but other quite surprising, the results that mathematical arguments provide. And all of these qualities of mathematics are what have made me so happy to have fallen into mathematics education as my life work. Thank you for listening. If you want a copy of the PowerPoint, email me at this address.
Okay, thank you very much, Professor Ussisky. You will give us a lot to think about regarding our beliefs about mathematics and mathematics learning and teaching. I'm sure the audience may have a lot, also have some questions or thoughts would like to share. And so now we will have around 20 minutes for a Q&A session. So if you have any questions or thoughts you want to share, you just raise your hand. We will bring the microphone to you. Okay. Who would like to ask the first question?
We don't bite.
Okay.
So you were talking about learning in stages, maybe sort of not being counterproductive in some ways, because some students maybe sort of go forward in some areas, and if you're doing it bit by bit, it kind of holds people back.
Just the fact that you used your hand this way.
Yeah.
That's stages. Interesting.
Do you think that there might be an idea that if they're teaching a primary, to teach all this level of maths and then this level of maths. Some students might be better at different types of maths. I'm not a math teacher, but that just struck me that.
I think there are students who think whether it's taught or not. We don't know what is, teaching begins at birth. And many parents really homeschool. In the United States, we have children who don't go to a public school or a private school. They're homeschooled. But there are many parents who send their children to school, and every minute at home, they're teaching their children in addition to the school. And that starts at birth. So we know that some students just seem to be able to abstract rather quickly and deal with abstractions. They deal with symbols very nicely. Other students have difficulty. Is that because they were taught that way or not? Even when you consider, this is a wonderful example of when you consider language, which we all learn, and you consider that somebody who comes from the United States to China, or somebody who comes from China to the United States, if they haven't had any Chinese or English, if they've only had one language, great difficulty. How do you learn the language? You don't learn the language by somebody talking to you in stages. You learn it by immersion. And if you're immersed in the mathematics, there are all levels of mathematics. Part of it is concrete, and part of it is with symbols, fairly formal, and part of it may be iconic. You have diagrams and arrows and things that help you. So when we think about learning, we realize, if you look at in general, I think your question was a wonderful general question. In some sense, you have to say, it's artificial to start just concrete, because life isn't just concrete, language isn't just concrete. Although with parents with children, we'll go, 1, 2, 3, 4. But parents, in some households, you go very quickly past the small numbers. You're going as far as the child will go. You will go, probably most in this room, went much further than just going, can you count to 10 by the age of 3? You realize there are numbers everywhere. And one of the things that sort of worldwide in mathematics is to beginning to limit the numbers that children get. Only up to 2 digits or 3 digits at the beginning. The world is not just 2 digits or 3 digits. The numbers you deal with in the world are lots of digits. And one wonders if you started, I know I didn't learn numbers, I learned big numbers fast. And the reason I know I learned big numbers at the very beginning, well before they were taught in school, was because my first book was an atlas. That had data, it had populations, it had geography in it, and it wasn't just counting. And I think it really influenced how I thought about mathematics, even though it wasn't mathematics, it was geography.
Do you think part of the problem then is, like you were saying about how it's just as difficult to learn a language, but English is used in other subjects like history or all the sorts. Do you think maybe part of the solution is to integrate learning maths outside of a maths class so that it's...
Absolutely. And I might say the avenue for some of this is statistics.
In history, definitely.
Statistics is a very good bridge.
Hello, I have a question on behalf of the student over there. Yeah. They don't know it yet, but I told them this is beneficial for them next year. So they're studying this program called Theory of Knowledge. And in that program, math is considered as area of knowledge. And an area of knowledge, mathematics is an area of knowledge. So they will learn it next year. So we often begin the discussion of mathematics looking into 2 different schools of thoughts, whether mathematics is discovered or is invented. So when you say mathematics is a language, it kind of like invented, right? But in the same thought, if it's invented, how is it possible for maths to describe the universe with that accuracy. So that is how we start off the exploration of mathematics as an area of knowledge. Maybe you can comment on this for the benefit of the student. Thank you.
I think in the last, let's say, 500 years, the scientific discoveries, been phenomenal. Not just for mathematics and for science, but for the world. Newton's discovery, why do things fall? There's a reason it's considered, it's in all history. But whether we find knowledge because we just generalize from experience or we invent knowledge, I don't know. It's a subtle distinction. We invent based on what we've seen. We don't just invent from scratch. We don't invent from nothing. Our perception would give us things that we would like to do. We would like to do things faster or more elegant or something. And I don't know, the answer to your question. I mean, that's why you have a full course. So in 5 minutes I'll describe it. No, I mean, of course I can't, and nor could I, nor would I, nor should I. But I think mathematics is unique in a way, in its strictness. In the strictness in which you can test whether something is true. And when you think of an example of this, think of the example of, I was giving this example to my wife last week, we were talking, that we have, Chicago is a city that's, first of all, it's flat. The city's very flat. And we have streets that are parallel. We have north-south streets that go north and south, and streets that go east and west, and they're perpendicular. And the whole city has these perpendicular, occasional diagonal streets, so that were the old paths before the city was there, and so on. But these parallel paths are not parallel, really. They're only parallel if you assume that they're in a plane, but they're not in a plane. They're on the surface of Earth. And if they're both going north, they're going to intersect at the North Pole. So every so often, what it really means is they're equidistant. The city has made them equidistant. And so, and I'm not sure where I'm going with this train of thought, but the point is that it's our perception, the strictness of mathematics, it allows me to talk about it that way. And I think that yes, there are people who get handicapped and they get straitjacketed by mathematics being so strict. But that's the power. You know the assumptions, and when we now know that there's spherical geometry, we know what the geometry of the sphere is. Okay, different assumptions. The only parallel, there really are no parallel great circles. There aren't parallel lines. You don't have one parallel to, one line parallel to a line through a point. Not on the surface of the Earth. It's different, and I think mathematics points out those. It makes you think more carefully. And statistics, as rough as statistics is, also makes you think more carefully. Is this likely to have been happened, or is it an outlier? Well, you can have outliers. Oh, it's likely, it's unlikely, but it still could happen, that kind of thing. Could a person actually guess all 50 questions on a multiple choice test and get them all correct? And you think the person is a genius because they got 50 out of 50. There's a possibility that they didn't know anything. They just went boom. But mathematics enables you, I think. It gives you the mind, the presence of mind to look at something that way. It doesn't give you the answers, necessarily, but it gives you a way of thinking. And I think that's the thing. And the fact that it has applications is the amazing aspect. Blame it on that.
Yes.
Okay. Did I say something wrong?
You said that applications make what goes on in the classroom meaningful to the outside world, and that kind of shapes what we know about the world. Does that mean that, what if we don't understand these applications? Will that cause kind of a language barrier? And kind of how would that in turn reflect on the learning stages that you were talking about?
Well, of course, you know, you can always, as a teacher, would pick, if you can have the opportunity to pick what you're going to teach. You obviously don't, you want to teach applications that are familiar to the students in a way. You don't want to teach applications to a sport, for instance, if it's a sport that isn't played in the community. Oh, I'll give you and for instance, in the United States, you wouldn't give an application to cricket.
Yeah, but like...
In Hong Kong, you would. But not in the United States. I'm just saying, you know, so you pick based on, if you're going to do an application, you want the reality to be there. Otherwise, it's not an application. Otherwise, it's just as theoretical as not having an application at all.
But what if you still don't understand the application? You know, is there like a language barrier in understanding it, or?
Well, you want to, you know, you want the interplay of the mathematics. I mean, we're talking about application of mathematics. You want the interplay between the mathematics and the application. You hope that it helps you understand both. That the application helps you understand the mathematics, that the mathematics helps you understand the application. And as an example, when a ball is batted, baseball is a big sport in the United States, but it's batted, and cricket, the path it follows is a parabola, unless there's wind. Wind can affect the path, but the path is a parabola. This is a big surprise to many people because they think the ball goes up and then kind of comes straight down. It doesn't come straight down. It goes, you better back up because it doesn't come down straight down. It's a parabola. So, I mean, that example where and so you look at the mathematics and say, oh, that's the way it looks in theory, that's the way a parabola looks. And here's what happens in practice. And you hope that it helps both the understanding of the application and of the mathematics simultaneously because they're together. I don't know if that answers you.
Yes, thank you.
Wait a minute.
To what extent should the areas of math be integrated into other fields of knowledge? What do you think? What would be the extent? Like, should there be a limit? Like, for example, say in language or literature-based subjects.
I think any subject to be meaningful needs to have connections to other subjects. This is the way we learn. Our brains connect things. We want to connect things, and I think, you know, if you do it with no connection to other subjects, it's sterile. It's sterile, you know. You go into the mathematics classroom and you say, oh, guess what? Reality ends here at the door. You know, I'm walking into this classroom. Here's where reality ends. I'm now at the whim of the teacher. I have no idea what's going on. I have no way to test this in the outside world. That's not something. I mean, so you really want never to make such isolation. And I'll give you an example, if I can give an example. One of the, as you may have guessed from some of the examples I gave, I'm very much into music. I was certified also to teach music as well as mathematics. And symphony orchestras play music that many people simply do not understand. They have absolutely no interest in this music because there's no connection that's made with their lives. It has no meaning to them. You want to make these connections. Orchestras are trying to do this with different kinds of programs and the kinds of music that they play and so on. And in some sense, they're applying the music to the world of the audience, the same way we're talking about applications here. So you have a symphony orchestra that's playing a version of popular music, and not just Beethoven, or do you know what I'm saying? So, and I think there's an analogy there. There's an analogy of how do you bring children who aren't, people aren't naturally going to learn about, they don't learn calculus on the street. You learn that in class. So you have to make some connections in order to make it real. And I think that's true of philosophy. I mean, if you're teaching philosophy, you want to give real examples. You don't want to just make it abstract. Otherwise, you're memorizing. Memorizing is not any way to learn something.
Are you saying that the extent that to which math should be applied to other areas of knowledge should be the amount that we're interested in how much practical use it can serve us, or?
I think there are natural ways in which mathematics fits into virtually any subject. But natural, you don't have to, but you have to have a disposition to look for those ways. I'll give you an example. One of my great interests, if you go to my website, if you go to, there's a website there, is in genealogy. Okay? Genealogy is an interesting thing. I had never seen the talk on the mathematics of genealogy, so I decided to make one up. And last year, for the first time, I gave a talk on the math. I never saw a talk at a mathematics conference or a genealogy conference on the mathematics of genealogy, which is very interesting because there's nice mathematics here. I mean, but one of the things that you have here is, you have two parents. And your parents had parents. It doubles. And each of those had parents, so there's 8 if you do the tree. There's 8, and then 16, and then 32, and then 64, and then 128, and then, oh my, it goes pretty fast. In 10 generations, you have 2 to the 10th ancestors on a tree. Now there might be some duplicates, but 2 to the 10th is 1024, so it was a big, go back 300 years more than that, and you've got 1 million people on the tree because each one of those had 1,000. Now you know the duplicates, lots of duplicates. Because if you go back even further, you have more people on your tree than there were people on Earth. So this is an interesting historical thing. I mean, if I were teaching history, this is something I would want to sort of mention. And then you say, okay, how many generations back are you going? How long is a generation? How do you measure how long a generation is? That's a statistical question. So you've gone from pure mathematics, which is how many are on the tree, to a statistical question, and that is how long is a generation? If you go 10 generations back, how many years have you gone back? It's around 300, a generation. People have done studies, statistical studies, in various countries of the world. That's what I mean by connecting. And I think it makes everything more meaningful. Makes school more meaningful.
Thanks. I think we only have time for the last question. And I already promised this lady here, so you can discuss later after the lecture, okay? Yeah. You are the last chance. Please, you are the last one. Yeah.
Thank you.
Oh.
Sir, I wonder the status of the ability of calculating in nowadays mathematics studying, because you know that the AI and calculators, they are fast and accurate enough to do the calculating. So does that mean we no longer need to work hard on improving this kind of ability ourselves?
Well, it seemed pretty clear that the learning how to, let's say, do long division, with multi-digit divisors and This is for, but you are, Professor Venn, you are, mental arithmetic or something, you're quite active in this area.
When I was a professor at the University of Southampton for 8 years, 2010, 2018, I knew long division was required to read for all schools in England. Long division is literally expressly required. Now with AI, I don't know. I can check, as the professor you mentioned, National Curriculum of Mathematics is published online. Most government publishes their mathematics curriculum online. But I guess you don't need to memorize, but you need to know the meaning of the division when you use it.
You need to know how to, that's just right. You need to be able to check. Checking the answer becomes even more important than being able to obtain it by yourself. And that's true of knowledge now in general, because AI generates knowledge. Checking that knowledge. What's a reliable source? Mathematics is helpful in a way because there are ways of checking it internally. You check division by multiplication, you estimate, there are a number of ways of checking. Where does that decimal point go? Where does it go when you do a long division? Where does the decimal point go? Does it go here, there?
So thank you very much.
Yeah.
I think for our students, audience here, do you have any suggestions how they can learn mathematics better? I mean, how to be a good student in mathematics? Thank you.
I'm happy to say I have no suggestion. I'm sure you're doing fine. Coming to things like this is, I think, very, very interesting, and very few classes get an opportunity to hear things like this, whether it's good or bad, but just the opportunity to hear somebody talk about the subject without giving you a problem, without effect. It's not on your homework assignment. You know, you don't have to know it. It's not going to be on the, I hope it's not going to be on the exam. Maybe it will be. On the exam, the next exam that you have. That's all.
Okay, thank you. I think now it's time for me to close the lecture of the day. Thanks very much again, Professor Yususki, for your such an inspiring talk, and also thanks all the audience for your